Thank you very much, everybody, for coming to the last session of the last day of OOPSLA. So today I'll be telling you about some of the work we've done on helping developers make sense of multi-threaded applications. And this is collaboration with Augustine, Paul, and Sasha. So performance bugs are really interesting because they don't always impact functional correctness, and they might compromise energy or make things really slow for people. And so they're really interesting because they're really difficult to fix. So there's been previous work, empirical work, that looked at performance issues and found that they take more time to fix, they require more experienced developers to actually handle them, and then in order to actually fix them, you have to change more lines of code. So in a previous work, a few years back, we actually did an empirical study of a process called performance comprehension, and we actually looked at developers at a company called WireTiger and tried to understand the kind of information that they need to collect, the kind of tools that they use, and the processes they follow to resolve performance comprehension and resolve performance bugs. And so for this, we basically looked at like 44 Jira tickets at this company and then interviewed a bunch of developers, performed quantitative and qualitative study. And what we found is that these developers spent majority of their time during performance comprehension looking at latency spikes. And they're really curious as to how thread activity correlates over time. So if one thread is doing something and then is blocked, then the fact that that thread is blocked is just mildly interesting. The interesting question is, what other threads are doing? What is it really waiting on, right? And then finally, they really were missing tools that would help them actually process very copious amounts of information that they would collect. So instrumenting a system is easy. I can get all my threads to output a bunch of data, but then making sense of it is the hard part. So there are kind of three requirements that we simmered this study down to that we believe would basically result in a tool that these developers would be happy with. And first of these is that they need to know when latency spikes occur. They need to be able to correlate activity between threads over time. And then finally, this tool would need to scale. Okay, so what does a developer today that's tasked with a task like this, what would she do? And so here's an example of RocksDB trace. This is a distributed database, a large database, and you have a trace of a couple of million function calls with 3 different threads. So one option is you could use flame graphs. This is a very popular tool amongst developers. You sample call stacks, and then you're going to merge them together, and you're going to display them alphabetically. Unfortunately, it doesn't show time. So the x-axis in the call graph tool is not time. And so you're going to basically mix 2 out of the 3 requirements. You will be unable to observe latency spikes. You won't be able to correlate thread behavior over time. But it does scale, which is really nice because you can ramp up or ramp down the sampling and therefore study really large software systems. Another example of a tool in this space is one that is very fine-grained. It's called Chrome Trace Viewer. And this will show you thread activity over time. And it will basically line up these threads into this nice interface. But if you were to run it on this kind of RocksDB trace, you'll be waiting for a long time. It would basically not scale to that kind of trace. So it would be able to show you latency spikes. You can correlate activity over time, but it wouldn't scale. I'll save you the other tools that we've looked at in this space. You can look in the paper for more, but essentially there's no tool out there that satisfies all 3 requirements, which is why we wanted to build a tool to provide this. So our solution is quite simple, actually. You start with this very massive trace, and our approach is that, well, if you want to study it, you actually don't care about all the details. What you want are the really high latency events. And so we came up with a compression approach. So the idea is that you're going to compress some of this trace in a very domain-specific manner, and then illustrate it to people, so people can actually observe thread behavior over time. So what does this compression actually look like? So again, you have a call stack sequence over time. This is massive, millions of call stacks long. What we're going to do is something that's inspired by flame graphs. We're going to merge these call stacks together, right? So we're going to have these patterns. Identical call stacks get merged. So here, a call stack containing A at the very bottom gets merged into a pattern. The other ones gets merged into yet a different pattern. And then we're going to arrange them and sort them. And we're going to sort them not alphabetically, as Wong does it, but sort them according to the order in which the first occurrence of the call stack appeared. So for example, the call stack containing just A at the very bottom was the first one and this trace at the top. And so that's going to be the first pattern that we're going to show. And the second one is going to be call stack containing P at the bottom that invokes Y, and so forth. So we arrange these call stack in this way, and we're going to retain the actual duration over time as well. So we're going to make sure that the length of the trace at the top matches the length of the encoded pattern as well. One thing you're probably wondering about, and why, what happened here, is that we actually lost precise ordering of function calls, right? So this is one thing that we're going to give up, unfortunately, because if you're trying to do some kind of compression, you're going to need to lose this information. You're not going to, well, okay, so the other bit that I mentioned is we're going to have cumulative duration of functions. So for example, this A appears 3 times, runs for a nanosecond each in the original trace, so it's going to be displayed as 3 nanoseconds on the bottom, so it's going to be to scale within this pattern. There is a loose causal relationship, so for example, A is always followed by P, for example, in the trace on the top. And so the same thing occurs in the pattern on the bottom. A is followed by a call stack containing P at the bottom. But this is very loose, so it does not generalize. So what would this look like for this RocksDB trace that I showed you earlier? Here's the actual visualization that we would produce. So time would go from left to right. It's really small on the screen, I'm sorry. You can look at the paper and kind of zoom in. We assign functions unique colors. Once we run out of colors, we can start using the color gray. So there's a lot of gray in this photo, and there's a lot of functions. You'll notice that it scales to this large input trace, but unfortunately can't find latency spikes with this tool, and time is going to be a problem as well. So there's one more addition that we're going to introduce, which is to actually leave long events alone. So instead of trying to compress all of thread activity using this regular rect_time expression, we're actually going to have a certain duration threshold above which we're not going to compress. Okay, and the intent here is that you want to retain the long latency events and the long latency idle periods, so that those actually pop out in your visualization, so the person would actually be able to notice them. And then the other things would be compressed. And then the second thing we're going to do is we're going to enforce a maximum interval of time that this rect_time expression can actually occupy on the x-axis. So for example, here you have no long duration events, but we're going to still use 4 rect_time expressions because we want to make sure that we're capturing these kind of gradual shifts in thread activity over time. And so we're going to encode them in 4 different ways. So if you do this for that original input trace, your diagram would start to look like this for specific kind of settings of these different thresholds. And you'll notice that you'll be able to observe this latency spike. It kind of jumps out because we're no longer compressing it. And you'll be able to see periods of idle time for the thread on the bottom. So the thread on the bottom actually has 3 periods of idle time that now are visible. One thing that you're giving up, unfortunately, when you do this, is that you're giving up linearity on your x-axis. So what this means is that the x-axis is no longer linear, as you'd expect. And then the other thing that you're maybe not obvious is that actually, well, the tool supports this kind of highlighting of different functions, but the different threads are linked to one another, and you can see that kind of using highlighting that I'm showing here in green. But they don't actually line up perfectly, right? Because we're compressing them independently, and they're compressed using these different nonlinear scales on the x-axis. So they actually don't line up anymore, right? So in order to line them up, you need to hover around to actually understand which periods of time in one thread correspond to periods of time in a different thread, okay? But we still have it linked, and so you're able to kind of identify these correspondences. Okay, so this tool satisfies, on paper, these 3 requirements. We can find latency spikes. We can observe thread activity over time and kind of find the correspondence between them, correlations. And we can scale to handle large traces. So the rest of the paper actually spends a lot of time talking about our empirical study to evaluate this tool in detail with users. We had 4 research questions that we asked. These are quite wordy because we're trying to be very precise. You can simmer them down to this, which is, first of all, does this tool actually help people understand what's happening over time? Second of all, what about these long functional latencies? Can people actually find these periods of latency spikes? Can people correlate activities? And then finally, does the tool mislead people on small traces? Because if we're compressing, if you use it for a small enough trace, perhaps it would actually be the wrong tool for those traces. So there's a long methodology that's described in the paper. It's a within subjects design where we recruited 42 participants. Each participant did 3 different tasks, and they did a study for about 2.5 hours. It's a very lengthy study. Out of these 42 participants, 7 were actually worked for MongoDB, which develops the wired tagger product. And then there were about 20 engineers that were participating that were experienced performance debuggers, meaning they had over 3 years of experience with performance debugging. More details are in the paper. We tested this tool with 3 kinds of traces. The normal wired tagger trace was the smallest one of about 1 million events. And then the larger ones had 50 and 40 million events across dozens plus threads. For the alternative tools, we kind of compared against this Chrome trace viewer tool, but only on the really small trace that it could actually scale to. We also compared against OOPSLA. OOPSLA is a interesting tool that basically slices up this long timeline into hundreds of smaller intervals that you can kind of inspect and then analyze. So it's very difficult to use unless you know where to look, essentially. And the 3 kinds of tasks that we had are here. Essentially, we had a question of comprehension over time, an outlier event task, and then finally, trying to correlate behavior. So we scored all of the responses, and then we computed the difference in the scores. And that's basically what I'm going to be showing you. So if the difference is greater than 0, the participants did better with our tool called NonSequitur. If the difference is less than 0, then they did better with the competitor tool. And if it was 0, it's going to be highlighted in yellow, then there was no difference. So for each of the questions, I'll kind of show you plots like this. And basically, you want to see more green and less red at the bottom. And so for the first question, which is what do threads are doing over time, you'll notice that NonSequitur was superior against this OOPSLA tool, against all the tasks and all of the developers. For question number 2, for finding these unusually long latencies, there are a couple of cases where developers would do better with the competitor tool, but for the most part, NonSequitur was dominant. It would also help people with correlating thread activities. That was quite superior to that. I think one reason for this is simply because of this linked highlighting. If you have more than 20 plus threads, the competitor tool, you just have to scroll around a whole bunch, and it's just very unusable. And then finally, for whether or not it misleads on traces, it's sort of a bit of a mixed bag here. Essentially, there's no difference between the tools. There's equal number of points above 0 as below 0. Of course, the reason you'd want to use this tool is for the compression ratio. So the logs that you're observing basically fit onto your screen. You don't have to paginate across. And so this is due to the fantastic compression ratio that we have, which is very lossy. So compression ratios are about 1000x to up to 33,000. So that's basically the talk. So studying multi-threaded traces, very complicated. You can collect a lot of information, but difficult to actually dig into it, and even fewer kind of tools that provide visualization support here in this space. So we built a tool that scales to large traces, helps you find outliers, and helps to inform you about correlation of activities across different threads. Thanks very much for your attention.
For questions, we have a mic, so just raise your hand. We'll bring the mic to you.
Anton, that's a question right here. Yeah.
Thank you for the talk. I was wondering, as the call stack seems to be quite sparse in general, would it make sense to keep the complete graph, to keep information about what are the collie and the color, and to keep the graph with the additive weight or all of the edges? and in order to retrieve some causal precision.
Oh, I see. So you mean perform compression in a way that you can still retain kind of causality to some degree, right? Yeah, I think the big challenge is really scalability of this algorithm, because even with this kind of compression technique, so basically it's linear in the scan that it needs to perform, but it's still quite like long running for long traces, and so any kind of like extra complexity that you're going to introduce is going to make it slower. So that's the main challenge. But I do agree that I think the promising bit about this work is that I think there's a lot of potential for domain-specific kind of compressions that this allows. So it'd be really cool to make it programmable. Yeah.
Other questions?
Hi, really cool work. So you developed this because you needed a tool to find something. So have you applied this tool to weird multi-threaded behaviors, and did you find something interesting that would have been almost impossible to find otherwise?
Yeah,
and so what?
Yeah, thanks. Yeah, so actually one thing that my presentation omits is the several case studies that we did. So we actually did case studies with developers at this wire target company where Sasha, who's one of the co-authors, consults. And so they've actually used this tool internally to be able to find these latency spikes. Yeah, so there's kind of description of it in the paper. I did not talk about it. Yeah, totally.
Other questions?
I actually also had a question. So I have two questions. One, what did you do in your evaluation? Was it questions on their perspective toward the tool, or was it more truly testing their understanding of the threading?
Yeah, it was really, all the three tasks were really about trying to get us to answer the research questions. So really focused on, so like here they are. So really in the context of each, because we had enough domain expertise to be able to formulate questions around activity of threads over time because we knew what the system actually does. So we would ask questions like, when this thread is doing the following thing, what other thread is doing this, Or when this thread is idle, it's blocking most likely on what other thread, things like that. So the questions are very precisely stated for each of the traces. And so they're very much focused on the kind of comprehension questions that people might have about traces like this.
I was also curious about, you said that the research question on whether or not it was misleading, I think
That's right.
was one of them.
Yeah.
Do you think that might have been part of the reason for that, maybe that you're reordering what was it? You were kind of
The call stacks.
collapsing.
Yeah, that's right.
So do you think that might be a part of it, or are there other aspects of it?
That's precisely the question that we wanted to answer, right? Is it the reordering that's really causing this, right? Because at that scale, essentially for small enough traces, you don't need to do compression, And so is this tool really necessary, And basically, does it handle the full range, or should it only be used for really long traces? And so we found it's kind of a mixed bag, right? Like there's more details in the paper, but essentially for this research question number 4, you'll see that there's some red spots where people have done better with Chrome Trace Reader, which is that kind of really fine-grained tool. But there's also points, kind of green points at the top, right, where they've done better with NonSequitur. So it's kind of unclear as to which one is preferred.
Thank you, Ivan.
Cool, thank you.